the work that Intel has been doing. And, people have already asked me the question a couple times, so I thought I would answer in advance that despite the fact that, I'm giving a presentation on ZFS, LDiskFS is not in any danger of going away. Lots of people use it. It still has, very good performance characteristics. And, I'm also a ext4, developer and contribute to ext4 quite a bit. And actually there's a lot of things that have been going on the ext4 side in terms of merging in features that had been developed for Lustre. And, a lot of them went in with when ext4 first was created. But in, the last, 6 months or so, a number of Lustre-specific features, went into upstream ext4 because I finally, convinced somebody that this is going to help them, right? Like large extended attributes, large, H-tree directories. And so we're actually getting, some good activity on the LDiskFS side. It just, don't worry that it's going away. Anyways, I think everybody's memorized that slide already, so I won't spend too much time on it. There's quite a few features that are going in to ZFS, and the ones on the left are already landed in the ZFS 0.7 release, and so for many people they may already be using this. 0.7 was used since Lustre 2.10.1, I think. The 2.10.0 release, I think maybe 0.7 wasn't quite out when 2.10 came out, but we had, built with preliminary versions. So you already probably have many of these features, and I gave a talk about this last year, so I won't spend too much time on that. On the right side, the ZFS 0.8 features, those ones are, currently, mostly already landed. The last two, when I've made my slide, actually there was 3 features that hadn't yet been landed for the 0.8 release. I was able to move down that bar so that there's only 2, well, not only 2, but 2 features that I'm very interested in that are scheduled for 0.8 that are still to be landed, but there's actually, this is active development, and so I'll go through what many of these features are. So it's worth mentioning what the different features or that come with each different version. So right now we're basing the various Lustre releases on ZFS 0.7, and the most recent release is ZFS 0.7.8, and we will be updating the maintenance, the LTS branch, and the master branch to track the latest ZFS stable releases. We don't actually track the development releases directly because if there's disk format changes and things like that, we don't want people to be using, a development version of ZFS with Lustre. Of course, you're always free to build your own version. We currently don't ship, ZFS binaries ourselves, but the ZFS on Linux project does. And, one of the things that that we're looking at for the Lustre 2.12 is that we build, we download the RPM packages from ZFS on Linux and build Lustre against the publicly available RPMs so that you can just pull down the ZFS on Linux RPMs, you can pull down the Lustre RPMs. They were all built happily together. You don't have to do anything, because right now you do have to do a little bit of module building yourself. And another good news, projection, let's say, is that ZFS 0.8 should be out relatively sooner compared to previous releases. So, there was a good period of time between 0.6 and 0.7, but the goal at least is sometime this September. There's a ZFS user group that's in September, I think it's developer conference. And so that's right in the same time frame as Lustre 2.12 will be out. And so if it's not out released by the time that Lustre is released, we will have at least done any work that's needed to build against that branch, so that people will be able to move to that and will be able to use that as the next release. Because there's, as I get to them, there'll be a number of features that people are quite interested in. So one of the great things, actually, in ZFS 0.7, multi-modifier protection. This is a feature that Lawrence Livermore developed. Well, the laboratory, not the person. This protects the ZFS pool from being imported on two servers at the same time. I mean, it's an environment that Lustre, almost everybody uses. Failover servers, and quite often with automated scripts that do failover. And while we would hope that established packages for high availability are robust, the truth is that they sometimes have problems. And importing a ZFS pool on two servers at the same time is really bad. I mean, LDiskFS, it can be problematic, but at least LDiskFS, the metadata is in the same locations. Typically, you'd have relatively localized corruption if this were to happen. With ZFS, because it's a tree-based structure, if you have two servers, that are writing correctly checksummed blocks that are, conflicting with each other, it can be problematic. And to paraphrase Bjorn Strustrup, who is the inventor of C++, he said, C++ makes it harder to shoot yourself in the foot, but when you do, you blow your whole leg off, right? And it's the same with ZFS. It's hard to corrupt your ZFS pool, but when you do, there's a good chance of significant data loss. So multi-mount protection, you have a periodic block, Uber block that's written to each disk, and when another pool tries to open it, it says, oh, this pool is actually being actively used by the other node. It blocks it, at the file system level. So, it's not meant as a primary form of high availability, but it, protects you in that last, belt and suspenders type mode. So this Lustre will enable this feature by default in Lustre 2.10 and later. Another good feature that came into 0.7 is the dynamic dnode size. And so this is something that we had large inodes in ext4 for many years, and that stores the extended attributes efficiently, so you can read the inode plus important extended attributes without doing an extra seek. And with ZFS, because the metadata structures are larger, we couldn't fit the Lustre extended attributes inside the D node. So every time you access a file, you have to do an extra read to get the Lustre layout. And even though ZFS does a good job of laying things out contiguously on disk, that can become fragmented. You don't change your extended attribute, but you do change a timestamp or something that ZFS writes the timestamp into a new location with the D node on a different spot of the disk. It hurts your performance. And so with the large D node feature, it's actually even more flexible than what's with LDiskFS. You can, instead of having external blocks like the spill blocks, you allocate multiple slots in the D node table, and so you get 512 byte increments of space, and then we can store a reasonable sized extended attribute. It's always going to be contiguous with the metadata for that file. And so again, this is enabled by default with ZFS 0.7 and Lustre. Another feature that came in kind of two stages is the improved quota accounting. in Lustre, earlier versions of Lustre since 2.4 when we first started supporting ZFS, the dnode accounting was handled at the Lustre level because ZFS didn't have a mechanism to do this. And so we implemented our own table to account for each user ID and group ID, but that added a fair amount of overhead. And we finally bit the bullet in ZFS 0.7 and implemented proper ZFS level dnode accounting, and using the same infrastructure that ZFS had for block accounting. And so that's already in the shipping release. What is newer is the project quota accounting. So LDiscFS got this feature, I think, in 2.9 or 2.10. And we put in the Lustre side of this support in 2.11. But we need the ZFS side, for it to work together so it detects when it's there. And once the 0.8 ZFS release is out, you'll be able to use project quota accounting with Lustre for ZFS. And it's worth mentioning too that the project ID handling, it can use the same tools it uses the same interfaces as XFS and ext4, and you can also use LFS project. There's a feature that DDN added so that they all use the same tools for managing quota, which is nice. As well, fault management and Z is handling hot sparing and things like that, device events, and this is something that you really need to have if you're going to use a large number of ZFS servers. I mean, it's one thing if you have 1 or 2 racks of disks, and one of your disks fails, you can look it up. Oh, which disk is that in the rack? But if you have a whole row of racks and you have 20 or 30,000 disks, as some large systems do, the risk of you pulling out the wrong drive is fairly high. So there's the Z integration can do automatic hot sparing and things like that. It can also integrate with the SCSI enclosure services, which is a standard Linux feature. If your JBOD enclosure supports it, and then you can blink the lights on the drive saying this drive is faulted or whatever, and then your operator with roller skates can go down the aisles and switch the drives efficiently. And another thing that people may have noticed from other presentations, that Lustre and ZFS performance on the metadata front has gone up significantly in the Lustre 2.10 and 11 with ZFS 0.7, and this is a joint project between Intel and Delphix, who are one of the leading ZFS developers these days. And there's a number of as an ogre would put it, you're peeling the onion, and it's a multi-layered problem, and a whole bunch of work was done to figure out where all the bottlenecks were, but put those together. Some problems on the ZFS side, ZFS has traditionally, while it's been a file-serving, file system, a lot of work has been done for database performance. You do all of your operations inside files, or what they call zvols, which are like block devices. They hadn't, focused on, how quickly can you create 1 million files. And so there are some very low-hanging fruit. I mean, before this project started, I don't know if I have oh yeah, I do have a slide. So before this project started, we were down at the, under 10,000, sort of creates a second. In some cases, 5,000 creates a second for the ZFS file system. And this is just, even the local file system was not faster than this. So this isn't a Lustre artifact, because LDiscFS could be doing, 50,000, right? And so through various stages of improvements with, on the Lustre side, you can see, you go from one Lustre version to the next, you're getting some improvement. You also get some improvement going from one ZFS version to the next. And, so we're up in the 100,000 range. It's worth mentioning that this is done with MDS survey, so this is only on the server side generating a metadata load. It's not a number of running with all the clients, because the guy who's doing the testing didn't have enough clients to saturate the server. But it's showing that, we're, an order of magnitude faster than we were, a year or so ago. And there are a few more features. I wanted to get an extension of this graph for the Lustre 2.11. It didn't get done quite in time. But so this is great news for ZFS. I don't have the slide that shows the LDiskFS performance. We were targeting, like, LDiskFS was at, when we started this work, LDiskFS was like at 100,000, but because we also made, LDiskFS faster through some of the Lustre improvements, our target, which, yay, we're as fast as LDiskFS now with ZFS, and now LDiskFS is like 150,000. So, that's not a bad thing, I guess. But it's good all around. So another interesting feature that has gone into ZFS is hardware compression support, and so there has been quite a bit of optimization in 0.7 for optimized checksums and things like that. CPU optimized checksums, CPU optimized RAID calculations and things like that are, quite a bit faster. This is also added support for the hardware acceleration for compression and encryption in the QAT card. And this is showing the BGI data. It's running, this is local ZFS performance. But yesterday I was talking about client-side compression. Doing the compression on the client is actually potentially better, but it's going to be integrated with the same, ZFS compression. So you would actually, have transparent handling. You could do decompression on the server side using ZFS if you wanted, right? So we're not just going to do a Lustre-specific compression. The block encoding is going to be the same on ZFS, whether the client or the server does it. And so, as you can see, it's 2 to 4 times faster than it's faster, 2 times faster than not having any compression, and can be a lot faster than if you're only doing CPU-enabled compression. And one of the features that went into 0.8 is disk level encryption, and there's also the same developer from Datto. He integrated the encryption engine, and so you can see not only do you get faster I/O throughput because of the compression, and I think Livermore, they've been even just doing the software compression gives them, I don't know, 1.5 or 2 times compression on their entire scientific data set. Right, so it's worthwhile. I'm not saying don't wait for compression until you get the accelerator, but there's a lot of benefit to be had just by enabling compression all the time with ZFS, and the accelerator reduces your CPU usage on the server. But if you got enough CPUs and they're idle, you could just enable this by default. The same group actually, this was done by some of the work was done by the University of Hamburg to have dynamic compression selection, so that if your CPUs are pinned and you're busy, it uses a lower level compression just to keep the throughput up. But if your CPU, you got a single threaded client writing, or you have more CPUs than you have I/O, it will crank up the compression level so that you can be more efficient I/O without slowing down the I/O. Right, and so that isn't landed yet. I know there's patches submitted, but some interesting stuff. The on-disk encryption that I mentioned, It's, anybody who's, who's worked with encryption knows that you should never do it yourself. Wait for somebody who's knowledgeable in the field to do it. And so a guy from Datto has implemented the encryption for ZFS and had it reviewed and things like that. And it's quite interesting because it's encryption. It's integrated into ZFS. It's not like block device encryption or anything. And the ZFS metadata is in plain text, right? So that you can do things like pool scrubbing, rebuilding your RAID. You can do backups and restores, of all the good features that have ZFS, verifying your checksums. But, the data blocks are encrypted and each block has its own key. They're encrypted in, Merkle tree, so you have to decrypt the top level and work your way down. And if there's problems with a key gets corrupted for some reason, the encryption is the corruption is minimized to only the block where the key is bad, and if you can't recover it from other backup copies inside ZFS, which has that functionality anyways. And it keeps blocks inside the cache. The persistent cache, they're still kept encrypted so that if somebody yanks out your flash device, it's not like you have all the plain text there, right? So it's fairly good. I mean, Lustre doesn't have a mechanism to manage keys itself. That's one of the things that I'd proposed with the IML developers, but there was a presentation last year about how do you handle key management for de-encrypt devices. The same thing would be true with Lustre. Is you only need to supply the key at mount time, right? So your pools would be protected if somebody steals your disks, but you don't have this ongoing key management issue. It's just when you first mount the Lustre OSTs, you'd have to supply keys. And so those could be kept in a central place, right? Lustre is not going to manage the keys. Another interesting feature that people have been wanting for ZFS is being able to remove a device after it's been added, because currently if you add a disk, even for a few seconds, there's any kind of I/O going on, some blocks gets allocated there, you can't pull it out of your pool again, right? And that's problematic if you make a mistake on the command line and you thought, oh, I'm going to add these 6 disks or 10 disks in a dual parity RAID configuration, and you made a typo on your command line. You actually just added 10 disks that are, have no redundancy, then you can't get rid of them. So they implemented the device removal. And because of how ZFS is implemented with the Merkle tree, it checksums, each block, and then all the block pointers that point to that block have a checksum. And then, each layer up the tree checksums the lower layers, because it makes it very robust. But you can't just take a block and say, oh, I'm going to rewrite the block pointer and move it over there, because now you have to rewrite every checksum up the tree, and every one of those that gets modified, causes this cascading effect. And it's hard to do. So what the VDEV removal did is create essentially like a virtual device that you copy all the data to an existing VDEV, and you make it seem like that it's like a loopback mount in some respects, where the old device is still there in name, but not in, it's there in spirit and not in body. And so as you try to empty out as much of that VDEV as you can, and what can't get moved because of snapshots or other references that exist, they get copied over. And as files get deleted or your old snapshots get deleted, the the virtual device shrinks down until such a time as you can hope that it disappears, or you only have like a stub header. It's a few kilobytes, and this gives you some flexibility with how ZFS devices are managed in a longer term file system. So one of the Intel features that we've developed is called metadata allocation class. And so it's the traditional Lustre versus metadata versus data segregation exists inside a file system as well. You have small metadata blocks and lots of them. You read and write them. They have wildly different lifetimes versus data blocks are larger. They may allocate megabytes, gigabytes of them at a time. So you really want to separate the management of those two types of blocks. And so the metadata allocation class can be thought of as mini Lustre inside of ZFS, right? And so what it allows you to do is segregate metadata onto a dedicated physical device, and that physical device can be SSD. Your regular data devices can be HDD. They can have different redundancy, so that your hard drives are in dual parity RAID Z2. Your metadata is on mirrored SSDs, and so you get a very different performance profile from those. And it optimizes a large number of operations. I mean, this is interesting for Lustre because you do, well, without size on MDS or something like that, you do ls minus l. You send one RPC to every OST to get the size, and now that one tiny read that you want to do is waiting behind 4 gigabytes of somebody else's job IO, right? And so you only want that one thing, but you got to wait. And so if that piece of metadata, the inode size and things like that, is stored on a flash device, it has a separate hardware queue, everything, PCI channel, it can be serviced very quickly, and the streaming IO can go on in its own way. Conversely, of course, the same with data on MDT, right? If you pull the small IOs off of the spinning disks, it also improves your spinning disk performance, right? It improves the allocation. You're only getting 128K, 1 megabyte, allocations on the spinning disks, and you can put, there's parameters that you can set to say, do I only want metadata on the metadata allocation class? Do I want to store small files, and how big do those files get, 32K, whatever. And so you can segregate a number of different aspects of your metadata. There's also a mode where you can do hybrid storage on, if you only have hard drives, you could partition a fraction of your disk as RAID 1 mirrors, and you still get the optimization that you don't have to do consuming a larger stripe width and interfering with the space allocation, having small blocks allocated in the middle of where you want to allocate large blocks. And the other big feature that we're working on for the Coral project is the clustered parity RAID. And this one is allowing you to improve the rebuild speed in case of a drive failure, so that typically you get a ZFS system today might have 3 or 4 or 5 VDEVs in them. They're 8+2 parity or something like that. One drive fails. When you're rebuilding, you're only using those 8 or 10 drives to do your rebuild, and the other ones are sitting there idle, hoping that you don't get a double failure. And with the declustered parity RAID, you involve all of the drives on that server in doing the rebuild. So you have 5 VDEVs, then you get 5 times speed up in your rebuild performance. And it does this by spreading, instead of having the RAID, only use the 8 or 10 drives in one linear fashion. It sort of does a pseudo-random allocation of drives for each RAID stripe. And you also, instead of having hot spares, you can have hot space. So it uses a fraction of each drive to store the rebuilt drive as a virtual space. And then because a portion of that hot space is on every drive in your system, your write bandwidth is a function of all of the drives in the system versus, you have one replacement drive, you only have the write bandwidth of that one drive, right? And so the virtual spares increase your write bandwidth significantly. You increase the read bandwidth by a function of the number of VDEVs, and this improves the performance significantly. So the graphical representation, if you say, like drive 5 has failed on the left, it's spread across, each of the parity stripes. If you look at it on the right, you see, it's sorted by drive index. All of drive 5 is dead, but if you map the numbers over, the yellow drives are the ones that are involved in rebuilding, each of the parts of the failed drive 5. So if you count up the columns, there's, 3 or 4 blocks on every drive that are being rebuilt. And so it, definitely helps your performance. The number of other features that are also of interest, ZFS OI scrub is a feature. Like we've had LFSCK for ZFS, for a few releases, but we didn't do any of the very lowest level repair on ZFS because we said, it's ZFS, it's never going to be corrupted, we don't need to rebuild it, but we can rebuild it if there's been an error. Not all of ZFS, but some limited number of errors. But also, one of the interesting features that came out of this is you're able to take LDiskFS file system, do some, it's not just a straight backup and restore. You do need to do a little bit of a process, but you can back up an LDiskFS MDT or OST and then restore it over to ZFS, and then it will rebuild all of there's a number of index tables and things like that, but it will rebuild it when you mount up Lustre again. Conversely, you actually can go from ZFS over to LDiskFS as well. And so that's kind of cool. Sequential scrub and resilver, if you don't have DRAID, this improves the rebuilding speed for existing ZFS file systems. ZFS channel programs, it's a new feature. I'm not quite sure how Lustre can use it quite yet, but it's interesting. It's essentially, they've built in an interpreter into the kernel, and you can give it like simple, delete 100 snapshots or something like that kind of command, and then it runs efficiently inside the kernel, and it can be all atomic versus, run this command 100 times and you have to wait for each one to complete, right? So I think there's some potential there, but I'm not quite sure how we would use it. And that's it. I think questions.